Here we will discuss free space propagation. So in free space propagation, there is a line of sight path between the transmitter and the receiver, or we can say there is no obstructed path between the transmitter and the receiver. And the received power in this case is proportional to the distance between the transmitter and the receiver, that is D. Next, to find the expression of the received power for free space propagation, we use Friis free space propagation model, which states that the received power at a distance d is proportional to the transmit power Pt, the transmit antenna power gain, the receive antenna power gain, the wavelength, inversely proportional to the system losses, that is transmission losses, fiber losses or antenna losses, and also it is inversely proportional to the square of the distance. So this implies that for a free space propagation model, the received power decreases with 20 dB per decade in logarithm. And the gain, antenna power gain, is represented by 4 pi AE by lambda square. AE is the effective aperture of the antenna. And if we increase the effective aperture of the antenna, the gain will also increase. But however, there are many other things related to antenna which are beyond the scope of this. So next is path loss. So this is the loss. This is the difference between the transmit power and the received power. And since transmit power is always greater than the received power, this is a positive quantity and this is usually measured in dB. So now the path loss is given as the difference between the received power expressed in dBm and the received power in dBm. And if we take the difference of dBm, we are left with dB. And when this PT and PR, they are represented in milliwatts. So path loss may or may not be a function of antenna power gain. So if they are function of antenna for free space propagation model, we will substitute the previous expression of PR into this path loss expression and we are left with this. And if the gains are included, if the gains are excluded, we assume unity antenna gain, then we are left with this expression. And if we talk about free space propagation model, this is a valid predictor of the received power at a distance t in the far field of the transmission antenna. Far field means that we are far from the transmission antenna. But however, if we see this scenario, it can be observed that if this d is equal to 0, then received power at a distance d is equal to infinite, which is obviously not possible. So this is not valid when d is equal to 0. So to improve upon this model, there is a closing distance d naught. This means, let's say we have a transmitter and a receiver. The distance between the transmitter and receiver is d, and we take a closing distance d naught. And the received power as a closing distance is PR d naught, which must be known a priori. So once this PR d naught is known, we can reference PR at a d to PR d naught. So that means once we have PR d naught, we can calculate PR d by just scaling the distances between this d and d naught. So this distance received power at distance d naught, this is calculated by taking several readings across this distance d naught and then taking the average across all these readings. And there is a condition on d naught that d naught has to be greater than the far field region or this df, which is the far field region or Fraunhofer region. It is represented by df is equal to 2d square upon lambda, where d is the largest linear dimension of the antenna aperture and lambda is the carrier wavelength. And to be in far field, this df should be greater than d, and df should be greater than lambda. So once these two conditions are satisfied, we are in far field, and this d naught has to be greater than df. Then the received power at a distance d is calculated by using this expression, where we know PR at d naught, which we calculated by taking several measurement across the distance d naught, and then after taking the average, we know distance d naught and we know distance d. And this d naught should be greater than Fraunhofer distance, and d naught should be sufficiently less than the actual transmitter and receiver distance. So now, to capture this large-scale propagation effects, two-ray model is the simplified model apart from this free space path loss model, which only considers the line of sight link between the transmitter and the receiver. That is free space path loss model. But two-ray model, it not only captures the line of sight path, but it also takes into account the reflected ray, one reflected ray between the transmitter and the receiver. So that means if this is the transmitter and this is the receiver, there is a one line of sight ray and there is a one reflected ray. Therefore, this is two-ray model because we are only considering two-ray. Yeah, in reality, there can be many more reflected rays, but this gives us some indication about the received signal strength. So we can get the electric field across the line of sight ray. We can get the electric field across the reflected ray. Then at the receiver, we took the vectorial addition of these two rays. And what we are end up is that the received power is equal to PT GT GR HT square HR square upon D4. So this shows that it not only depends upon the transmit power or the antenna power gains, but also captures the height of the transmission and the receiving antenna. So it also captures the effect of how this received power varies with the height of the transmitter and the height of the receiver. And before, in free space path loss model, we saw that the received power is inversely proportional to 1 upon distance square. But here it can be seen that received power is inversely proportional to the distance raised to power 4. So this indicates that after taking only one reflected ray, there has been sufficiently decrease in the received power compared to the free space path loss model. For example, we can say that if the received power decreases by 20 dB per decade in free space path loss model, but now with the addition of one ray, it is decreasing by 40 dB per decade. That is much faster than the free space propagation model. So in general, we can say also there are not a single ray, there may be multiple reflected rays. So we can say that received power is inversely proportional to distance raised to power minus alpha, where alpha could be anything between 1.4 to 6 depending on the operative environment, and the path loss is directly proportional to the distance raised to power alpha.